to record. Yeah, please start.
So first of all, thanks for inviting me to give this presentation. This is a topic which is really taking my attention and on which I am working hard and hopefully I'm making some progress. So this is based on a paper I was submitted a bit more than a month ago, written together with Luc Darmet, and in large part in work in progress, which has not been published yet. Let me introduce the idea or what we hope to reach in this research, recalling the story of the axiom very quickly. So, first of all, we should notice that whenever you solve a theoretical problem, okay, you advance in science, you have a deeper understanding, and often you have unexpected and surprising new implication. But in general, you also discover new problems that previously were not known. This is what happens with the story of the axiom. In QCD, before 1975, there was a problem. It was called by Weinberg the U1 problem. And it was why the eta particle does not behave as a ninth Nambu-Goldstone boson, but it has a mass which is sizably larger than the pions and the kaons. With the discovery of instantons, and with understanding of the properties of the vacuum of Yang-Mills theory, the problem was solved. It was understood that the U1 axial anomaly in a non-trivial vacuum background has no conserved axial current, and thus therefore there is no Nambu-Goldstone boson, as experimentally verified. However, with this success, a new problem came into QCD. The fact is that when you have to account to transition between vacuum component that have a different winding number, you have to add a term, a theta term to the QCD Lagrange. Then in the path integral, this automatically takes into account these different type of transitions, but it brings in QCD P and T violation. That is CP violation. Phenomenologically, you know from the measurement of for searches for the neutron dipole moment that the parameter theta should be extremely small, less than 10 to the minus 10. This is a very unnatural number. It's hard to believe that it's just the result of a chance. And moreover, it should be noticed that it cannot be justified, such a small number, in terms of anthropic reasoning. Saying, okay, our universe needs such a small value, otherwise it would not host observers, or the cosmos would not look as like we know it, because in fact values of theta, even as large as 10 to the minus 1, 10 to the minus 2, we live our universe as we know it, not modified. So that's really a fundamental problem. Switch. Sorry. Okay. There is a solution that was put forth a few years, a couple of years after the problem was brought to light. And it's called the Peccei-Quinn symmetry solution. It works basically in this way. The mechanism transforms theta into a dynamical field. And a dynamical field with equipped with a potential such that at the minimum, the value of theta is 0. So it gets rid automatically of the offending term. The mechanism predicts unavoidably a quasi-massless scalar, the axion. It was a bit later found that unexpectedly, the axion has also the right properties to account for the dark matter. So the axion was not invented to be a dark matter candidate, but it results that has really good properties to be a cold dark matter candidate. Unsurprisingly, the axion raises new problems. The mechanism relies on a global symmetry that must be spontaneously broken and anomalous, but whose origin is unknown. This symmetry must be respected to a very high degree of accuracy, and this is related to the tiny value of allowed for the theta parameter, very small value. So any small breaking of that symmetry will produce a theta larger than the phenomenological limit. A question is how this symmetry can remain preserved up to the required operator dimension, which is around 10. We know that there are accidental symmetries, global, also they are not spontaneously broken, but that's not the relevant point in the standard model. But we know that they are broken at dimension 5, and this is lepton number. Let's say they can be broken at dimension 5, or at dimension 6 in the case of baryon number. So if the axion exists, this problem must be solved. It is then conceivable, because this is what the story tells us, that the solution to this problem could shed light on other unresolved issues of the standard model. And this is the line of thought I want to follow. The basic ingredients, very quickly, for the Peccei-Quinn solution. So we need a scalar potential invariant under a global U1. So you transform scalar fields with a global phase, and the potential must remain unmodified. This symmetry must be broken spontaneously, which means that you can replace phi with a vev, that is the order parameter of the spontaneous breaking, and a nonlinear representation of the Goldstone boson, which is given by the field divided by the scale of the breaking. This is the Goldstone boson, so it is a field with no potential, and it enjoys, for this reason, a shift symmetry. So it enters only in a derivative way. So you can shift the field by a constant, and your Lagrangian for the axion remains unmodified. Then you need couplings between scalars and some quarks, so particles that have non-trivial transformation under a SU3 color. This is, let's say, the original coupling in the high energy theory, is a renormalizable Yukawa coupling. At the low energy theory, you replace phi with the vev and with the exponent of the Goldstone boson. So this term can also carry the rephasing symmetry if you assign suitable chiral charges to the quark field that will basically respect this condition. The symmetry, however, must have a mixed U1 SU3 anomaly. That's why we need coupling to the quark, which means that the sum of the charges of the left-handed quarks minus the charges of the right-handed quarks must be different from 0. Why is this? This is because you want from this term to go in the basis of the real masses, so where the quark fields are well defined, you can write propagators and so on. And to do that, you need to redefine the fields with a space-time dependent redefinition. Since the symmetry is anomalous, you bring out a term of the phase of the redefinition, which is a local phase, times GG dual, that are the field strength tensor of QCD and its dual. So the theta term is transformed in this way with the addition of this dynamical part, and the shift symmetry allows you to get rid of theta without changing anything else in the Lagrangian. And then it can be shown that non-perturbative QCD effects generate a potential. Look, this coupling is not derivative, so it's breaking the original symmetry. It's the only term that breaks the original symmetry, so eventually it will generate a potential, and this potential has the property that minimizes when the Axion field goes to zero. The scale of the potential is fixed by QCD and can be written as m pi s f pi squared. Now let's describe the problems. So the Peccei-Quinn symmetry is anomalous. This rephasing symmetry must be anomalous. So it's not a fundamental symmetry of the theory. With this I mean that the generating functional, which describes completely the theory and would solve the theory if we were able to carry out this integration, has no trace of this symmetry, is not invariant under a Peccei-Quinn transformation. Moreover, in benchmark Axion models, where phi is a simple complex scalar and gauge singlet, I can write renormalizable terms like mu cube phi, mu square phi square, mu phi cube, lambda phi 2 therefore. These terms are allowed. They do not break any gauge, local gauge symmetry. They do not break Lorentz because phi is a scalar, so they are not forbidden. However, any of these terms would completely destroy Peccei-Quinn invariance and would completely spoil the solution to the strong CP problem. There is more. Even if you decide that you don't write this term, which would be in any case an unusual choice, non-perturbative quantum gravity effects are, there is consensus that they will still generate terms of this form. This is found when you can study controlled solutions. And this is the case of Euclidean wormholes. These are a semi-classical but non-perturbative configuration you can find in quantum gravity. And the problem was studied first by Kalos and collaborator in '95, and more recently by Alonso Urbano and Alvin Escudero. There is a consensus that those terms do arise with a scale, which is the Planck scale to the cube. This also is not surprising. We see that in QCD, non-perturbative effect give a potential that is proportional to the lambda QCD, to the fourth power, not inversely proportional. And here it happens something similar. The terms are weighted with the action of the configuration that gives rise to the breaking of the symmetry. Now, this action is found to be of the order of log m Planck divided the Peccei-Quinn breaking scale. So this is not a so large log. Its value is order 15. And to get rid of this term, or to keep this term under control, we would need a configuration with an action around 200. So we are far from that. This means that this is a real problem. That's not the only problem, because now imagine that you find a way to enforce invariance in the renormalizable Lagrangian, but you have to take into account the fact that there might be effective operators that break Peccei-Quinn symmetry. The second aspect of the problem is usually denoted as the quality problem. So consider this effective operator. So phi to some power with some scale to just get dimension 4 overall and a coupling G. We have to require that the energy density of the effective operator, which is this, must be less than 10 to the minus 10 the energy density of the QCD potential. That is the condition to ensure that QCD will dominate the choice of the vacuum value of the Axion. or of the dynamical theta. To give an example, if this coupling is order 1, if lambda is the largest scale that makes sense to take in a quantum field theory, that is the Planck scale, and if the Peccei-Quinn symmetry breaking occurs around 10 to the 10 GeV, which is right in the middle of the preferred range, which is between, let's say, 5 in 10 to the 8, 5 in 10 to the 11 GeV, we get that the dimension of the operator should be larger than about 10. If we appeal to the fact that those operators might come with a small parameter, a small coupling constant, small because it's related to the exponential of the axion of a wormhole configuration, you gain just 1 order of magnitude, because log m Planck VA, and 1 order not of magnitude, sorry, one order in the dimension of the operator. So instead of fighting with dimension 10, you fight with dimension 9. There is a last problem that I mention only because it can have some relation to the solution of the first two. So the Axion scale, as I just said, should be larger than about 10 to the 8 GeV, and this comes from phenomenological limit on axion coupling to matter. So this is a large scale compared to the electron wheel scale, and this means that the potential that breaks the Peccei-Quinn symmetry can contribute to the problem of electron wheel stability. This problem is much larger than, I mean, the axion gives only a contribution to this stability problem. There are other standard model completion which involve new large scale, like the seesaw mechanism, gags, and so on, that also bring in a problem of electroweak stability. Nevertheless, if we can keep, as I will show in the last slide, really, of the talk, if we can find a solution to this problem, the problem not of the electroweak stability, but of the contributions of the Peccei-Quinn mechanism to the electroweak stability, we also have automatically a solution to the origin and quality problems. A sample of proposed solutions. So it's commonly accepted that it would be satisfactory if a Peccei-Quinn symmetry arises automatically as a consequence of first principles. Typically, the first principles we can use are Lorentz symmetry, local gauge symmetries, and a suitable field content of the theory. However, spontaneous symmetry break requires vacuum expectation values. So we need scalars, because we cannot give a VEV to particles that carry non-trivial Lorentz representation. Otherwise, we would break Lorentz symmetry. So fields that host the axion must be Lorentz singlets. We are then restricted to consider local gauge symmetries as a tool to enforce automatically a global U1 symmetry. This is by far not an exhaustive review, but I just mentioned that discrete gauge symmetries that were introduced in model building by Krauss and Wilczek in 1989 have been often proposed as a solution. So you assign to the scalar field that hosts the axion a charge under a Zn group. The first Peccei-Quinn violating operator can arise only at phi to the nth power, given that this is the group. This, of course, requires that n should be 10 or larger. So we need Z10 or a larger discrete group. a different approach, which is based on a continuous U1, a continuous Abelian symmetry, local, introduces two scalars with two charges. The sum should be larger or equal to 10. Is again the same 10 that ensures sufficiently high dimension of the Peccei-Quinn breaking operator. Q1 and Q2 should be relatively prime. In this case, the first operator that violates the Peccei-Quinn symmetry is given by this combination. This is the first U1 local gauge invariant combination. And as you can see, because it's Q1 at the Q2 and Q2 at the Q1, and there is a dagger here. So this is gauge invariant. Again, we find this explicit 10, which enters the requirement. Another attempt is using non-Abelian gauge symmetries. Take, for example, a symmetry SUN cross SUN, and a scalar multiplet that transform under in the B fundamental of the group that hosts the axion. Imagine to write this scalar multiplet is a square matrix in the singular value decomposition. You have here a unitary matrix, n times n, a diagonal matrix of what are called the singular values, another n times n unitary matrix, special unitary. Both are now a special unitary because I have extracted here the phase of the determinants. And this is in fact a parametrization which resembles the typical parametrization of the complex scalar field. Now you have rho plus v, and then you have the Goldstone boson, the nonlinear representation of the Goldstone boson. And it's very useful when you deal with some matrix fields. If we take n larger than 4, the renormalizable potential for this symmetry is very, very simple. There is a trace term, this one, and what is called the adjugate term. This is the trace of the minors of the matrix Y dagger Y. This is the second invariant. The first is written like this to trigger spontaneous breaking. This invariant can come with a coupling positive or negative. The explicit way to write it is t square minus trace Y dagger Y, Y dagger Y. So it's clear that this potential has an automatic rephasing symmetry. I can send Y into a phase times Y, and the potential is invariant. The anomaly in this case should come from KSVZ quarks, because I need to put them in n-dimensional fundamental representation. So this is a simple coupling, and these quarks are not the standard model quarks, but new exotic quarks, standard model singlet, presumably. Now, the first offending operator is the determinant of Y. You see, if you take the determinant of this object, you get an invariance because special unitary matrices have determinant 1. The dimension of the determinant is n. So again, we require that the symmetry should be at least SU10 cross SU10 or larger. Can we do any better? Well, if we consider only the problem of finding a potential with a suitable global accidental invariance, this is easy. So we take a local gauge symmetry, SUM cross SUN, with only the requirement that M is different from N. I take, for definiteness, M larger than N. And then we take a scalar multiplet in the B fundamental of the group. Special unitary invariants can be constructed with Kronecker delta, which correspond to the unitary required condition, and Levi-Civita epsilon, which correspond to the speciality of the group. So determinant equals +1. The delta invariance can be read off the characteristic polynomial of y dagger y. So if you write the characteristic polynomial, you write in terms of some coefficient ck, which are precisely the trace of the minors of order k of the matrix y dagger y. I write in this form, which looks a bit formal, because it makes apparent that all these coefficients carry an invariance, no, a rephasing invariance. They are all Hermitian and they respect an accidental U1. Epsilon invariant, that are the ones that could be that are in general non-Hermitian, so they would violate this invariance, there is none. And there is none because to make a singlet of the SUM, so I need a Levi-Civita with M indices and M field components. But then all these field components carry an N index. But since N is less than M, somewhere I need a repeated index. So somewhere there will be the same component with this, well, there will be a component with the same index under SUN, unavoidable. Such a combination vanishes symmetrically because epsilon is totally antisymmetric. So already a simple symmetry like SU3 cross SU2 yields a potential that enjoys an automatically an exact global U1. Here just a remark, for a square matrix n times n, that's is the worst possible case. In this case, I can contract the left index with a Levi-Civita and the right indices with a Levi-Civita because the dimension is the same. And this is nothing else than the determinant that I showed before. So because if I switch to field components, I switch two indices in two Levi-Civita, of course, this combination does not vanish symmetrically. So this type of symmetries, accidentally enforced, is peculiar of what I call rectangular symmetries. Symmetry with M different from N. So the question now is, can these symmetries be promoted to Peccei-Quinn symmetries? It would be great if it is possible. Let me note at this point that there is a connection between Peccei-Quinn quality, if we want to use an Abelian symmetry, and flavour. Flavour in the sense, in the large sense. So any non-Abelian gauge symmetry generating a Peccei-Quinn symmetry is a flavour symmetry. If I imagine new exotic vector-like quarks, okay, it will be flavour of this vector-like quark. Flavour in the sense that there are transformations of the non-Abelian group that change one quark into another quark. If I have to consider the standard model quarks, then they are electroweak chiral. I cannot have a renormalizable operator if I put a dynamical field. So I have to couple the field that breaks flavour, that carries flavour, and the Higgs, two scalars, two fermions, dimension 5. But in this case, the symmetry is properly what we would call in the standard model a flavour symmetry. So following this line of thoughts, we are led to consider models of flavour with a generic structure. There might be vector-like quarks with a renormalizable coupling. Then we have to couple the standard model, or in general chiral field, electroweak chiral fields. There will be a certain number of multiples transforming under the rectangular symmetry, and possibly there will be higher order operators, where these new scalar insertions can be constructed by contracting indices of the fundamental fields. So we have to keep our mind open that if we follow the Peccei-Quinn quality, we should not be shy to introduce new quarks and possibly more than one scalar field. So standard model quark masses and mixing then in this picture would be generated dynamically by specific valve configuration of the scalar fields. We, of course, will look for hierarchical singular values. Singular values are the diagonal values of the diagonal eigenvalues of y dagger y, for example. This is possible. In some years ago with Chi and Fong, we showed that one can get all the standard model hierarchy, mixing, and even the CP violating phase out of a spontaneous breaking of non-Abelian symmetries. We were not looking for an Axion, in that case, or for a Peccei-Quinn quality, but we know that such a picture can be phenomenologically viable.
Excuse me.
Yes.
So, Enrico, so in this Lagrangian, which fields are standard model fields and which fields are new extra fields?
So where you see here a renormalizable term, they must be extra field. In this case, I will come back to this model. In this case, what I have done, I have put the standard model doublets, quark doublets, in SU4. So I have my 3 doublets plus 1 additional doublet. Then to have a renormalizable coupling, I need a right-handed doublet. So this is a term that involves an electroweak doublet here, an electroweak doublet there. And so it can have an insertion of a multiplet and no Higgs is needed. Here, I have my doublets that instead couple to the down right quark. Well, to a triplet, of course, of down right quarks. This coupling carries SU2, so I need SU2 of electroweak. So I need to couple to the Higgs. That's why this is a dimension 5 operator, and here there is 1 over lambda to take into account the correct dimension. The same happens here with an up. This contains, for example, just the charm and the light up quark. And the reason of this is that I want to implement a rectangular symmetry. So if this is a quadruplet, of doublets, this is a triplet. So this carry SU4 on the left, SU3 on the right. This carry SU4 on the left, SU2 on the right. Now, I'm talking of flavor symmetry now. And then I have what presumably could be the top right, that is again coupled to all the doublets, and this Z will carry just SU4 because U3 is a singlet. This is not a model. This is just a picture of what we are looking for. Some structure that will distinguish some quarks, for example, the top from the charm and the up, because this is the requirement of a rectangular symmetry. And that might contain additional quark. I mean, the hope is that enforcing this idea will tell you how many generations you need, and if you need additional vector-like quarks, just to protect the Peccei-Quinn quality. I have to say that this is just a theoretical attempt. The flavor problem in the standard model is persisting, is there since 40 years. I believe that we cannot claim that there have been really breakthrough, great advancement in the understanding. And we should also notice that the amount of data has been increasing a lot, both in number and in precision. So nowadays we know with high precision the value of the mixing angles. We have discovered the charm, then the bottom, the tau, we have discovered the top. So more information came in, but the flavor puzzle remains, and I don't think we have been making big progresses. One attempt would be to find theoretical consistency, so try to find a theoretical part of the theory which we understand a bit better, and that will feed inside the flavor problem. This is one attempt. If I wanted to, if I believe that the axiom exists, then I need a Peccei-Quinn symmetry. If I have a Peccei-Quinn symmetry, then I need scalars coupled to particle carrying color. We do have those in the standard model, they are the quarks. Then I have the problem of protecting the Peccei-Quinn symmetry. I believe a good way is using non-Abelian local symmetry. Immediately I'm led to consider theories of flavors of the standard model quark, of flavor of the standard model quarks. That's the line of thought. So the guiding principle is that the Peccei-Quinn symmetry of the required high quality must arise automatically from a suitable flavor group and from the field content. So we go back, but our U1, accidental U1, can be promoted to Peccei-Quinn symmetries. It's easier to illustrate an exercise here. Assume a simple symmetry, SU3 left, SU2 right. Take a scalar multiplet in the B fundamental, and take a triplet of a left-handed quark. Now, these are not standard model. Imagine they are KS-Vuzi exotic quark. So we have a triplet of left-handed quark, a doublet of right-handed quark, and we need to introduce an additional right-handed quark because we need to match left and right to avoid color anomalies, gauge anomalies. No? So I call this additional quark T right. A matrix 3 times 2, there is always a rank which is the smallest number, whether they are the rows or the columns. So the rank of Y 3 times 2 is 2. Rank, it means it has only 2 eigenvalues. So we have one massless quark. We are forced to add an additional scalar multiplet. The simple way is to add a triplet. So a triplet to the SU3 singlet of 1. Then the mass, the structure of the Lagrangian from where the quark masses arise is the following. Here I have the left-handed field coupled to the doublet of right-handed, and then I have an additional coupling to the third quark, right? From these two fields, I can write two renormalizable mixed invariants. And I need mixed invariants because the potential for Y will have a rephasing U1 symmetry, the potential for Z its own rephasing U1 symmetry, and I want to break this symmetry to a single U1. So I call the first invariant, which is constructed with Levi-Civita, I epsilon. You see, I can saturate now all the three SU3 indices, and with another Levi-Civita, the two SU2 indices. So this is an invariant, dimension is 3. This is invariant under a U1 symmetry where the sum of these charges twice the Y plus the Z is 0. Then I have another invariant which is built by contracting the indices of SU3 with a delta. So it's a Kronecker delta. So I call this I delta. This is, you see, the contraction of the SU3 indices. And then these two indices are contracted with an SU2 tensor. I concentrate only on non-Hermitian invariants because those are the invariants that can perform this breaking. No, if they are Hermitian, then they do not carry any charges, so they do not contribute to any breaking pattern. This operator is invariant if I have this charge relation. Clear, because z dagger y, so the difference of the charges. So since these two relations are incompatible, then one would say that the symmetry is completely broken, and then there is no residual U1. Does this mean that there is no Peccei-Quinn solution, that we should stop here? No, it's not so, because we need to consider the vacuum structure of the scalar fields. So here I write the singular value decomposition. I can perform gauge rotation, so gauge away U3, gauge away V2, and I end up with a wave structure which is of the following form. This is the analogous, the nonlinear representation for the complex scalar field. I would like to do the same for the Z field, but since I already gauged away U3, this U prime free is left. So the form of the Z field on the vacuum will have, in general, Z1, Z2, Z3. And this can also be complex. And that's not relevant. The scale of the breaking is given by the trace of y dagger y, in the case of Vy, the trace of Z dagger Z in the case of Vz. This is the correct normalization of the Goldstone. Now consider the non-Hermitian part of the potential. So this has the first invariant with some coupling, and the second invariant with its own coupling, plus the Hermitian conjugate. This combination can be always recasted as the cosinus of some dynamical phase and the modulus of the invariant and of the coupling. If we go on the vacuum, since this is a modulus, is definite positive, the cosinus always like to go to -1, because that's the way you minimize the potential. So that's why I'm writing this non-Hermitian part as minus the vacuum expectation value of this operator and minus the vacuum expectation value of that operator. Now, those vacuum expectation value want to be as large as possible to lower the potential. But if you look a moment at the structure, you see that the epsilon term, if I have y1, y2, so I have here y1, y11, here y22, that's my choice of the basis, and this choices forces Z to concentrate all its length on the third entry, Z3. In that the way I maximize this invariant. Conversely, since the delta invariant involves the contraction between the scalar product, maybe not very appropriate, but basically it is like a scalar product between the two multiples, it's maximized when they are aligned. So when Z1, Z2 are aligned with Y1, Y2. Clearly, I have, it's not possible to maximize both. And here, in this case, I have really two options. So I have two symmetry breaking patterns with two different maximal, two different little groups. They are the maximal subgroups of SU3 cross SU2. This, for example, will preserve an SU2 vector built up with this SU2 and the SU2 containing SU3. And these will preserve an SU2 cross SU2, and this will preserve an SU2 vector times AU1. It doesn't matter. The important point is that given the value of these two couplings, I will go into this background vacuum or into that. So In this vacuum, I delta is 0, clearly. While if I go in this vacuum, is the I epsilon, which is 0. So on the vacuum, only one of the two invariants will survive, which means that the corresponding symmetry will not be broken by the other invariant. This was studied already in 75 by Georgia and Pies. So the idea is that operators for which the vacuum expectation value vanishes do not break the symmetry of the vacuum. Thus, the vacuum can enjoy a larger symmetry than the Lagrangian, and the scalar bosons associated with these symmetries remain massless. They are, so to say, a different type of Nambu-Goldstone bosons. We should also recall that U1 symmetry breaking operator exists. I can write them in the Lagrangian. So they do not break the gauge symmetry. This means that QCD can still produce a potential that, while respecting gauge invariance, will give a mass to these massless bosons, because operators that break the symmetry can be written down in a gauge invariant way. So we can easily identify the Nambu-Goldstone boson, I use the same name, that remains perturbatively massless and hello? Can you hear me?
Yes.
It disappeared my presentation. Wait a moment. Sharing, resume share. Okay, sorry. I don't know what happened. So I decide to take the vacuum determined by the epsilon invariant. So the charges are related in this way. The Goldstone boson is this one. This 2 is related to Z2, so that's the way you identify the Goldstone boson. What we would say is the Axion decay constant, VA, is related in this way to the original vacuum expectation values of the two fields. Please take a moment to notice that this 2 elevated to the square gives a dominance of this wave over that wave. So the scale here is fixed by the sum of the square of the order parameters weighted by the square of the charges of the field. This will be important for the last part of the talk, if I will ever get there. So that ensures that the for given shifts of the phases of the fields, the Axion the Nambu-Goldstone boson transforms with the correct shift symmetry. Can this yield a viable model? Well, here is the problem. Recall that this is the structure of the wave of the Y field multiplet, and to ensure a mass of top right, we need to choose this option. So the epsilon invariant was chosen to have all the quark massive. That is, Y and Z must be misaligned to give masses to the free flavor of quarks. The vacuum is identified by this and by this condition, and we have this charge. Let us now compute the anomaly. The anomaly is the sum of the left-handed charges minus right-handed charges. So it's 3 times the charge of the triplet minus twice the charge of the right-handed doublet minus the charge of the top. I can recombine this expression in this way, but xq minus x little q is nothing else than the charge of the Y field, and this is nothing else than the charge of the Z field. So I see that I reproduce with the anomaly exactly the condition that I had derived from the invariant, that is, this symmetry is non-anomalous. So while this wave breaks U1 to an accidental symmetry, which is exact, protected, this symmetry is non-anomalous. So it's not a Peccei-Quinn symmetry. And the massless Nambo-Goldstone boson does not solve the CP problem. The question is this just an unlucky accident occurring with this group, or is a general feature? This is a very recent finding. It dates not older than 10 days ago, when we finally understood what is going on. So consider a generic gauge symmetry, which has a product of left-handed groups and right-handed groups, which act on a certain set of scalar multiples in B fundamental. So a set of Y. These are not group indices, these are names. This is the scalar that transform under SUM left, SUN right. So then I have n left-handed and right-handed quarks, where n is the sum of the dimensions, is the sum of the dimension of the various groups weighted with the multiplicity possibly of some isospin, electroweak isospin. So they must match, no? I need the same number of left-handed quarks and right-handed quarks, again for QCD gauge invariance. So we can write a certain number of invariant quark scalar coupling, Q bar, Y, Q, eta are constants, and we should put H over lambda when needed, when this is a chiral combination we have, but this is not relevant. So now we assume that all quarks acquired masses. So the determinant of the big mass matrix is different from 0. Under this condition, it can be shown that for any global U1, there exists at least one scalar operator, is a combination of the field, with a non-vanishing wave, this is important, and a charge equal to the U1 SU3 anomaly. So we can show that you can always write an operator which must be non-vanishing on the vacuum that has a charge equal to the anomaly. So since we want a non-zero anomaly, we need an operator that breaks on the vacuum the symmetry. No, it's not avoidable. Second point is the modulo the coupling constant, this coupling constant here. The vacuum value of the operator is related to the determinant of the effective Yukawa coupling. The Yukawa coupling that you read off the standard model after the dynamical field have acquired the wave. I will not show because still it's a bit complicated, the proof of these two statements, but they are indeed correct. So first one, point 1 implies that any anomalous U1 suffers explicit breaking at least at dimension n. This provides an upper limit on the possible quality of Peccei-Quinn symmetries that are protected by non-Abelian local group in general. 2, this implies that the source of breaking is removed as the determinant goes to 0. So if you put a Yukawa coupling to 0, you are not constrained by this, let's call it theorem. This provides an unexpected connection between Peccei-Quinn quality and Yukawa hierarchies. So hierarchies are beneficial to protect the Peccei-Quinn quality. Small Yukawas render this determinant small and render the vacuum expectation value of the offending operator accordingly small. I will skip because my time is almost over. This was a brief description in this with this symmetry of the way the hierarchy are generated. That's really fun. They come out so naturally. But I want to close with my last slide, describing shortly a different approach. So this approach is based on considering what is the Axion scale and what is with respect to the compact space radius in which the axion lives. So consider the usual lexical head potential for a complex phi that hosts the axion. The radius is VA, and VA is also the order parameter of the Peccei-Quinn symmetry breaking. So with VA, we have associated the phase transition, maybe primordial gravitational waves. The axion compact field space has radius FA. I call it FA. In this simple picture, it's clear that VA and FA are the same because this is the radius. So the axion runs around this bottom with radius VA. Conceptually, however, there are different quantities. When the axion is hosted in more than one scalar multiplet, so take many scalar multiplet with many would-be Goldstone bosons, the axion is defined in this way as the ratio of the particular waves, and these are order parameters, divided the scale of the compact space, where FA is defined by the sum of the different waves weighted by the square of the charges. You remember, we already found this. So this is because this is the expression that correctly gives you the correct periodicity of the axion. So the axion is spanning this space, 2 pi Fa, where Fa in the multiscalar model is given by this. So Fa can be much larger than the single waves in case the charge are large. This is called the clockwork mechanism. Consider now a realization of this mechanism protected by a local gauge group. I take this gauge group is a string of SU3 cross SU2 with scalar field that are singlet under the first SU3 and then are doublets of the SU2 and triplet of the next SU2. And then I have what we could call the bridge fields, sigma, that transform under 3 different subgroups. I make it short. You can write a potential in this way. Yn comes twice. Sigma, it will result that sigma carries no Peccei-Quinn charge, and Yn plus 1. You see that this gives a condition that the charge of this field is twice minus the charge of this field. If you have a long enough string of this operator, you reach the last field with a charge which is exponentially larger than the charge of the first field. Now, if matter, the standard model of the quark, let's say coupled to just to the first field, so that their charges are small, because we start with a charge which is, for example, 1. All the interaction between the quarks and the axion are suppressed exponentially by the value of the charges. So the axion decaying constant gets this factor. There is a sum, and in the limit in which all these waves are of the same, you get a factor of 4n plus 1 from the sum. I conclude here the result is that all axion interactions are suppressed as needed as 1 over Fa, and Fa is large. But the waves can be of order 100 GeV if n is large enough. 20 is a bit uncomfortable. But why this solves the quality problem? Because now V divided in Planck is 10 to the minus 17. So already operator of dimension 6, when suppressed by the second power of this ratio, are safe, do not contribute to the potential of the axion in a dangerous way. So I mentioned this construction. This is in our paper with a bit more details, just because it is a realization of the clockwork mechanism as an accidental symmetry. Most of the papers that treat the clockwork mechanism are imposing a global symmetry that behaves in this way. While in our case, our rectangular symmetries are able to produce a potential that has a clockwork U1 as an accidental symmetry. It's just, let's say, model building. But of course, again, we are dealing with uncomfortably large numbers. Summary and conclusion, I think I am almost on time. So the Peccei-Quinn mechanism provides an elegant and convincing solution to the strong CP problem. However, in my opinion, we do not yet have a similarly elegant and convincing model enforcing this mechanism in a natural way. We could say maybe that we have a mechanism, but we don't have a theory for that mechanism. The scalar potential that breaks spontaneously the Peccei-Quinn symmetry can automatically be U1 invariant and protected from dangerous higher dimensional Peccei-Quinn violating operators only if the scalars transform under some local symmetry. I should change this only because just in the previous slide, I showed that there is also another option, that of distinguishing the scale of the Peccei-Quinn breaking from the scale, from the radius of the compact axion space. So preferentially, let's say, if the scalars transform under some local symmetry. This symmetry could be abelian, continuous, discrete, or non-abelian. Non-abelian symmetry have the nice feature that they can be directly interpreted as flavor symmetries, whether for KS-WZ quarks, in that case is not very interesting, but in the case of standard model quarks can be very interesting. A certain type of symmetries have particular interesting feature with respect with U1 Peccei-Quinn symmetry protection and connection with flavor hierarchies. So far, they suggest that some quark masses should have a different origin than others. Additional vector-like quarks are most likely needed. So we need to boost a bit the determinant of the Yukawas of the quark. Some vector-like quarks is really welcome. This, of course, implies some violation of CKM unitarity, which, by the way, it is what it seems is observed in the CKM element involving the up quark. It involves some flavor gauge bosons with not too large mass, because we have ordered parameters that should give mass to the top and to the up. So if we take VA as the scale of breaking, which is maybe 10 to the 8 GeV, there should be masses which are suppressed as M up over M top. This brings you in the range between 10 and 100 TeV. So we expect gauge bosons in flavor gauge bosons in that range. And with this, I have concluded my presentation. Sorry if I broke by 5 minutes, but thanks for your attention.
Thank you very much. So now is question time. So is there any questions?
I guess it was very clear and convincing.
Hello, hi. I have a question. How are you? Yeah.
I'm fine, thank you.
So you introduced non-Abelian flavor symmetry in your talk, and is it possible to choose a flavor symmetry in a compatible way with the minimum flavor violation assumption or not?
That's built in.
Independent?
Because, yes, that is built in the approach, because minimal flavor violation is the statement that any source of flavor violation are proportional to the standard model Yukawa coupling, are aligned with the standard model Yukawa coupling. This is there is only one source of flavor violation here, which is the spontaneous breaking of the flavor symmetry. So this is giving the Yukawa couplings of the standard model, and any other source. Let's say we bring the spurions that have been used to elaborate techniques based on the minimal flavor violation paradigm. Here are real fields. So we have really the same spurions. So this is minimal flavor violation, by the way. It is really the potential that produce minimal flavor violation.
And about the mass scale of this vector-like quark, how low can they be?
These, I think, can be repeated what I said about the flavor gauge bosons. So you need that these multiplets of scalar will have hierarchical entries. If you want, if you hope to explain the standard model hierarchy. The typical scale, which is the largest scale, the scale where the Peccei-Quinn symmetry is broken, it should be of the order of what required by phenomenology, between 10 to the 8, 10 to the 10 GeV, something like that. But then you need some entry in the matrix, which is hierarchically smaller as the top mass was related to the up quark mass. So what I would guess is that you will have vector-like quarks at the Peccei-Quinn scale, and other vector-like quarks which are suppressed by a factor, with a mass suppressed by a factor 10 to the minus 5, which is the up quark mass divided the top quark mass. So if you take 10 to the 8, there should be vector-like quarks at the 1 TeV. That is order of magnitude expectation.
Okay, thank you.
You're welcome. By the way, you asked two very interesting aspects of all this construction. One, can we have something around the corner? I would say yes. Between few TeV and few tens of TeV, we expect to have some population of gauge boson, maybe with vector-like quarks. And the second is correctly the connection with minimal flavor violation that I forgot to underline, but it might be nice to make a clear statement about it. So thank you for your questions.
Okay. Any other question? Okay, if there is no more question, then let's thank to Professor Enrico Nardi. Thank you very much.
Thank you very much.
Thanks to you, and thanks for your invitation. Thanks once more for your invitation.
Okay, Enrico, please send your slide to email.
Yes, I will send a PDF. I hope it will be not too large. Okay, I make a PDF. I will send you in a few minutes.
Okay, thank you.
Thanks to you.